Okay, so what we're going to do today is we're going to lecture on chapter 20, which is basically what the first part of the lab is about for today and tomorrow as well. So that way we'll be able to do the lab, hopefully. And so we started with chapter 20 last time, where we talked about transition metals. I got a little bit into transition metals. And really the purpose of sort of talking about transition metals, as we talked about last time, is really we're going to be talking about mainly in this chapter, when we really get kind of into it, is complex ions. And complex ions are basically a lot of times transition metals sort of in the middle, and they're attached to a bunch of ligands. And a reminder that a ligand in this case is a Lewis base. And remember that a Lewis base is really something that can donate a pair of electrons. So as we'll talk a little bit about a little later on in this chapter as well, again, typically things that are really good sort of Lewis bases are things that have maybe negative charges because they gained electrons. Also things that are polar and have non-bonding electrons that they can sort of transfer those electrons over. That's also why when we think about complex ions, as we'll talk about, it's really sort of thought of as a more Lewis acid sort of base situation that's going on, as the metal here, the transition metal, is typically going to be an ion. And because of that, that's electron deficient. And because it's electron deficient, that makes it a really good Lewis acid. And a Lewis acid is obviously something that can gain some electrons. And obviously, things that have a positive charge are deficient in electrons. So that makes them a really good sort of receiver, if you will, of those electrons. Now, some of the things we talked about in terms of transition metals last time, in terms of some of the trends, we talked about Z effective, and that's the effective nuclear charge. And again, that is really the charge that is felt on, say, the outer electrons, for example, like your valence electrons, because of what is referred to as shielding, as we talked about. So the lower energy electrons, which are the core electrons, are closer to the nucleus. So they essentially will kind of shield the higher energy electrons, which are further away from the nucleus, from the full brunt of the positive charge that you find in the nucleus. And what that's going to essentially allow is those outer electrons, or those valence electrons, to essentially be held less tightly. So they're not held as tightly because, again, I think we did lithium as an example last time, and lithium with its +3 charge in its nucleus from its 3 protons. Again, those kind of core electrons are going to feel that full sort of +3 attraction. And again, sort of electrostatic attraction, positive and negative attraction, increases with charge size. So that's going to be a fairly strong attraction between those electrons and the nucleus, as opposed to our sort of outer valence electron, which is going to experience some shielding from these lower guys. And we could calculate it, as we talked about last time, +3 charge in the nucleus, -2 shielding electrons. Essentially, what that valence electron out on the outside there is only feeling is sort of a +1 attraction to the nucleus. The result of that is that it's not going to, again, be held as tightly. And that's really why we see, one of the reasons why we see that the valence electrons are, again, involved in bonding. In general, the effective nuclear charge increases as you go to the right and decreases as you go down. And again, as you go to the right on the periodic table, we have a lot more protons. And because they have a lot more protons, even the outer electrons are going to feel a stronger pull to the nucleus because there is a greater positive charge to begin with in the nucleus. That also affects things like we also talked about, which is size, right? So atomic size is affected by that. That's also why we see, one of the reasons we see that as you go up and to the right, size decreases and it increases as you go kind of left and to the right. And again, for that reason, there's a lot more protons in the nucleus as you go to the right. Again, even though there is some shielding that's happening because there's a greater amount of positive charges, that's going to bring even the outer electrons in closer to the nucleus, and that's going to overall affect the size of the atom. Now, we were talking about obviously transition metals, which obviously is between group 2 and 3 on the periodic table, right, is our transition metals. And again, a lot of complex ions have transition metals as sort of the centerpiece of them. And they are, as we talked about, the D block, right, on the periodic table in terms of electron configuration. The first two groups is the S block. Obviously, 3 through 8 here is the P block in terms of electron configuration. And those two rows on the bottom there is your F block in terms of electron configuration. So we kind of finished up, excuse me, last time talking about electron configuration, and a reminder that if you know, obviously, an s orbital could hold 2 electrons max. A p subshell, because there's 3 of them, could hold 6 electrons. D subshell, because there's 5 of them, could hold 10, and an F subshell, because there's 7 of them, could hold 14 electrons. And really kind of where each of these orbitals begin. Remember, on the first energy level, you only have s orbitals. On the second energy level, that's where you first start to see p's. On the third energy level, that's where you start to see d's. And on the fourth energy level, that is where you see f's. So we get 1s, 2s, and you can just fill in the numbers as we talked about towards the end last time. And this will give you really sort of the proper order at which electrons go into the atom. And again, you can fill in the numbers here, and even if you go too many numbers, you'll never get there anyways, but it don't matter. And we got something like this. And remember, we always start up on top here, and we just kind of zigzag back and follow the arrows. One of the things, again, a reminder that as the electrons get filled into the atom, the s orbitals are lower in energy than the d's, so they do come first. So we do put the electrons there into the s's first, and then start to fill the d orbitals up. There are a few exceptions to normal electron configuration. Probably the two most common that people are told to remember is chromium, which is 24, and again, copper, which is 29. Again, the exception is with the S, we have one less electron up in the s orbital and one more electron there in the d. And the same sort of exception happens for copper. Again, it has one less electron in the s and one more electron there in the d. And remember, this is sort of noble gas configuration. It's kind of a shorthand for electron configuration. It does need to be the noble gas that comes right before the element you're writing the electron configuration for to put in there. As I also mentioned, if you look on the periodic table, kind of below chromium and below copper, and kind of come in, there's a lot more exceptions like that. Again, something like PD there has no electrons in its S's. They've all been basically sort of promoted upwards. And they're able to do that because, again, these guys are very close in energy to begin with. And as we'll talk a little bit more about here in a second, when we actually do start to fill the d orbitals, there's actually a switch in the energy level of those orbitals, and the s actually ends up being higher than the d once you start sort of promoting some electrons into the d. Questions on any of that there? So then let's talk a little bit about ions and what happens with transition metals when they do obviously make ions. Obviously, they're in the Ds, and as the electrons go in, as we just talked about, they definitely do go into the 4s first, for example, for the first row transition metals. And again, we start to fill. But once you do start to sort of promote in some electrons there into the d orbitals, there will be this switch in terms of energy. And what ends up happening is those 4s electrons, for example, will actually end up being higher in energy than the 3d. And that's really sort of important in terms of when the transition metals go to lose electrons. Now, as we know, usually when things lose electrons, they will lose their valence electrons. So transition metals will always basically lose the s electrons first. And then, if necessary, they will continue on and lose some d orbitals, electrons, if they kind of need to go in there. And that's what we see here, for example, with Ti. And again, it's 20, was that other 22, I think. And when this makes a +3 charge, that means that it has basically lost 3 electrons. So when the electrons go into Ti, they will go in like so. But now there will be that switch that will occur. So what will happen is we will end up with this guy higher in energy than our 3D. And now when this Ti goes and loses 3 electrons, it's going to lose these 2 first, and then it needs to lose a third one out of here, and it will end up with argon 3D1. That is also why when you look at transition metals, they also, when we talk about valence electrons, equals the group number. So if you look at the group number for transition metals, that will give you your valence electrons. It is the normal kind of, if you want to think about 1 through 18 numbering, or really kind of 3 through 12 numbering. So when you get into that transition metal region, it really is kind of like the 3 through 12 numbering will give you the number of valence electrons. So if you look at something like Ti there, which is like right here, it's number 4. And again, that is the 4 valence electrons that it has. It has the 2 for the S and the 2 for the D as well, which gives it its 4. Same thing, if you went all the way down to zinc, it technically would have 12 valence electrons, even though it'll never lose 12 valence electrons. But it technically has that many valence electrons. That's also why transition metals are a little bit different than sort of representative metals. Representative metals, like in group 1, 2, and 3, when they lose electrons, they end up back at the noble gases that come before them. They hit that noble gas configuration. Typically, transition metals, when they lose electrons, will not end up at a noble gas, because if you look at something like zinc, would need to lose like 12 electrons. And again, we don't typically see zinc with a +12 charge. It has a +2 charge typically, is what happens in that particular situation. Any questions on that there? So if we had something, for example, like iron, and iron is number 26, and if we write the electron configuration for iron, again, it would be technically 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Again, this part of it up to here is 18, which you can shorthand as argon 4s2, 3d6. And again, if you look at it, it is in iron is right about here, and that is group number 8 if you look at it. And right here, the 6 and the 2 there are its 8 valence electrons that you have for iron. Now, when iron, for example, makes a +2 charge, it has lost 2 electrons. So once again, always with the transition metals, what's going to happen is we are going to lose those 2 s electrons first. And the configuration here would be argon 3d6. So something like iron with the +2 charge has 6d electrons available to it. Now, if iron went to a +3 situation, it would then lose 1 more electron. So since it's already Giving away its s electrons, it would then have to delve into the d, and that would give you argon 3d5 in this particular case. And that would be having 5 valence electrons. One of the important things in this chapter when we talk about complex ions is you definitely will need to be able to calculate or figure out by writing the electron configuration how many sort of valence electrons that a transition metal ion will have so that you can distribute it. Question? CRT, it's just found experimentally to be more stable with an extra electron in the d orbital versus the s. And again, they're able to do that because they're really, really close. And there's a lot of those sort of experimentally found more exceptions. A lot of it has to do also with some of those rules that maybe you remember from electron configuration, like Hund's rule, where it kind of maximizes parallel spin. It's kind of really stable and stuff like that. So, you know, some of that has to do with it, but it's just been found experimentally. Those guys have those things. Have other questions? I would say for us, probably, just so you know, though, as I mentioned, if you go like between copper and chromium down on the periodic table and kind of in, silver is an exception, PD is an exception. There's a ton of actual exceptions in that sort of area between those guys on the periodic table. I say most of the time when you take chemistry, chromium, copper are the two that most people make you kind of remember and stuff like that. But in reality, there actually are a lot of exceptions kind of underneath those guys on the periodic table. Other questions? All right, so why don't you try one? Why don't you do, let's do, I don't know. Let's do Mn with a +4 charge, and why don't you do nickel with a +2 charge? Why don't you write the electron configuration for both of those? Mn is 25, and nickel is, we got there. Okay, let's take a look. So here we're going to go Mn +4. Mn with no charge has 25. So that would technically be argon, again, which would get us to 18. 4s2, 3d5 in this case. Again, if you look on the periodic table, Mn is group 7 there, and that is the 7 valence electrons that it's got going on. And in this case, when it makes a +4 charge, once again, we are going to get rid of our s's first. So that is 2 electrons. In this case, we then need to go into the d here to take the other 2 out. That's going to leave us a argon 3d3. So in this case, it would have 3 sort of valence electrons in this one. Any questions on that there? Yeah. It doesn't. You could write it all out if you want. Yeah. So obviously the argon would represent the first 18, you know, through there, through 3p6 basically. Yeah. You do, because what happens is, as we talked about, when the electrons go into the atom, they do fill into the s's first because they are lower in energy. But once you start sort of populating the d orbitals with electrons, they're very close in energy to begin with, so there's this kind of switch in the energy of those orbitals. And what ends up happening actually is the s ends up being higher in energy than the d, and that's why we take the s's first. And that happens with all transition metals, so you always kind of take the really the first 2 groups there, group 1 and group 2 guys, you take those electrons out first. That's also why sometimes you may see online or something like that, people write electron configuration, and it looks like, for example, it's all in order, all the 3s are together and all the 4s are together and all that kind of stuff. And that's usually when people write electron configuration based on energy rather than filling order. And that's how you get that. But most of the time when you write electron configuration in classes, we do it based on filling order. So that's why we write the 4s first and then the 3d. I've only done it once in one class where we wrote it the other way based on energy, but most people do it based on filling. And filling, S gets it first, but then there's a switch that allows those S's actually to be higher in energy. Other questions? All right, we look at nickel here, which is 28. So again, a little argon, 4s2, 3d8 in this case. And once again, this would be nickel with no charge, neutral. And again, if you look up there, nickel there should be number 10 on the periodic table there, if you count it. And again, that is technically is 10 valence electrons. Here, once again, we're going to lose 2, which is what the plus 2 means. So we are going to get rid of just the 4s in this case, and we will be left with argon 3d8 in this case. Any questions on how to write electron configuration for transition metal? Again, quite important, as there's going to be a section of this chapter where, like I said earlier, you do need to kind of figure out to begin with sort of how many electrons there are in the ion valence electrons so that you can distribute those electrons properly, and something we're going to talk about. All right. So let's talk about some other sort of properties, transition metals that you may be familiar with. Oxidation states or oxidation numbers. For the most part, this is the first row, transition metals. You do see a lot of plus 2s and plus 3s are very common. You can see that as you go from left to right, it sort of maxes out, if you will, in terms of Mn. Mn has a lot of oxidation states, anywhere from plus 7 to plus 2 it could be. Again, very common, plus 2s, plus 3s, as you can see on most of them. Then it kind of comes back down a little bit, the oxidation state, as you go to the right. Ionization energy is another sort of trend that's important. A reminder that the ionization energy is the energy that's required to remove an electron from the gas phase of an atom. So when we talk about ionization energy, we oftentimes are talking about really cation formation. Again, those guys that make positively charged. As you hopefully know, or maybe remember, electrons do come off one at a time. They don't all just drop off at once. So for example, magnesium would lose 1 electron and become positively 1 charge. In order to do that, that is what is sometimes referred to as the first ionization energy. And that's the energy basically to remove the first electron. Then magnesium with a plus 1 charge will dump off a second electron, for example, become plus 2. And that would be known as the second ionization energy, the energy that's required to do that. And then maybe it will lose a third electron here. And that would be the third ionization energy. So in general, as you may guess, as you go from, for example, losing the first electron to the second, to the third, or however many you're going to lose, it gets harder and harder to remove those electrons once you've already lost an electron. Because if you think about what happens when you make a cation and you lose those electrons, everything shrinks, right? The cation is smaller than the neutral atom, and that's because you lost electrons, you lost electron density in the cloud there, so everything gets closer to the nucleus. So now those remaining electrons have now moved themselves closer to the nucleus, which means they're going to feel a stronger positive charge, and they're going to be held tighter, which means if you're able to get rid of the next electron, everybody's going to shrink in a little bit more. And again, the more and more electrons that you lose, the harder and harder it is to sort of remove those electrons. So in general, when we talk about going from like the first ionization energy to the second, to the third, and so forth, the ionization energy increases as you continuously lose an electron. It takes more and more energy to try to remove an electron, and it gets harder and harder to remove those electrons along the way. In general, on the periodic table, if you look at the first ionization energy, it increases as you go up and to the right and decreases as you go down and to the left. So in general, first ionization energy increases to the right, decreases to the left. Now, when we look at something like that, we can actually see this on this table. For example, if we look at magnesium, which I just did there, to remove the first electron is 735 kilojoules of energy per mole. Gets much harder to remove the second one. you're up to 1400. You almost doubled the amount of energy needed to remove the second electron, again, because now it's closer to the nucleus. And when you want to go to the third, you can see you're now almost like maybe a 5-6 fold increase in terms of energy to do so. And that really doesn't happen, for example, with something like magnesium. And that is because if you look at the electron configuration for magnesium, looks something like this. And right here are our two valence electrons. So after we get rid of electron number 1 and electron number 2, those are our two valence electrons. When we try to go to that third electron to remove, we're now into our core electrons. And energy-wise, it's not efficient for that to occur. And that doesn't happen, for example, for something like magnesium, because now you're into the core electrons. You're not going to be able to remove that. That is why something like magnesium has a fixed positive charge of +2, because it will only lose those valence electrons. It will not go and dip into its core electron. Same thing if you look at sodium. We know sodium makes a +1 charge, and it has one valence electron. 495 to remove the first one, then you're almost about tenfold the energy difference to remove the second. The second one at that point is a core electron. Again, not going to happen. Why something like sodium has a fixed positive charge. Also why, for example, transition metals can make variable charges, because you're not going to get necessarily into those core electrons because they have a lot of valence electrons, right? They have anywhere from 3 to like 12 valence electrons. So they have a lot of ones on the outside, which allows them to have different sort of oxidation states and different charges, which is why we'd use like Roman numerals, right, when we name those things, because copper could do +1 or +2 in the situation here. And again, if you look at something like aluminum, why it's a +3, 580 for the first one. Again, getting harder to remove the second one at 1800, removing the third and last valence electron at 2700. Then you can see the pretty big jump as you try to remove that core electron. You go from like 2700 to like 11,000. Again, not energy efficient. Again, why something like aluminum will kind of tap out there at the third electron and a +3 charge. Any questions on that there? Here are some other sort of properties, again, in terms of our transition metals. Atomic number obviously increases to the right as we have more protons. Electron configuration we see here with our atomic size getting smaller as we go this way. Our first, second, and third ionization energy getting larger, but also increasing as you go to the right as well. Again, as you can see, most common +2, +3 charges, and we do see a slightly increase in density as you go to the right. Again, greater mass, smaller volume, and those are just some of those trends there. Here are our ionization energy between first and third. Third much higher than the first. Again, harder to remove that third electron. There's our second in between there. Another important trend is electron affinity. And electron affinity is really the energy change that occurs when somebody gains an electron. So when we think about ionization energy, we think about it in terms of making cations. With electron affinity, we think about it in terms of anion formation. And that is, again, the energy change that occurs when somebody gains an electron. In general, trend is it does increase as you go up to the right and decrease as you go down to the left. In general, it's not a perfect trend. As you can see here in group 7, it kind of increases as you come up, but then kind of comes back down a little bit. So it's not a perfect trend, but it is generally increasing to the right and decreasing left. Electron affinity should not be confused with electronegativity. They are different things. Electronegativity is the ability of an atom to bring electrons towards itself, right? And as you hopefully also remember, that increases as you go up and to the right and decrease as you go to the left and down, with fluorine being our most electronegative element you could have. So electronegativity is that ability to kind of bring electrons towards itself. When we talk about electron affinity, that's again more of an energy change that occurs once it gains electrons. Things with high electron affinity means it likes to gain electrons, is able to gain electrons really well. And that also corresponds a little bit with electronegativity, as is a similar trend. The only way you can kind of gain electrons is to bring electrons towards yourself. So obviously, it's something that's able to kind of bring electrons towards itself as well. All right. This is a table of the first row transition metals of relative abilities here. And what we see here is reducing ability and increases as you go up. And you may be saying to yourself, well, these are actually when we have greater reducing ability, this guy is most likely going to be the one that gets oxidized. And you may say to yourself, but isn't the one that's more positive going to be reduced? And the answer is yes, except that all these are not standard reduction potentials. These are standard oxidation potentials, as these are all oxidation reactions. So these are all oxidation reactions, different than the SRP table that we've been using in the last chapter. If you flipped all these reactions around, that would reverse the sign on all these, and then it would follow what you might remember. And here, this guy actually is the most positive SRP on the bottom, and that is the guy that would be most likely reduced on the bottom here. So again, this is an oxidation reaction, opposite of the reduction reactions we took that. As we talked about as well, again, the atomic radius starts to decrease as you go to the right on the periodic table. And here's what the first row transition metals look like, in case you're curious. This is stuff you don't have to worry about anymore. Don't worry about that. And again, you can see these are some different oxidation states that these transition metals can make. And depending on oxidation state and what they hook up with, they will have some different colors. All right, so now that we reviewed a little bit about transition metals and some of the ions, let's talk really about the heart of this chapter, which is coordination compounds, where we do find a lot of these transition metals in the complex ions. So a coordination compound is typically consists of two things. It will consist of a complex ion and a counter ion. Now, you could think of coordination compounds as like ionic compounds, if you will. And just like in ionic compounds, there's a couple of things that we typically follow. The positive guy first, followed by the negative. And that is also true in coordination compounds. So when you write formulas for coordination compounds, or you give names for coordination compounds, that is what you do. You follow the kind of positive first, followed by the negative. And when we talk about a coordination compound, it does contain both of those things, a complex ion or a coordination or a counter ion. And depending on the situation, you could have a counter ion that is positive. And if you do, what that would mean is your complex ion is negative. Alternatively to that, you can have a complex ion that is positive and a counter ion that is negative. So as we will see in this situation here, you can really have one of each. Again, the counter ion is really just there just to balance out the charge of the complex ion. Now, a complex ion is a ion that has a metal in the middle, and as I mentioned before, typically speaking, it is a transition metal that's in the middle, and it's bonded to one or more molecules or ions. And again, those molecules or ions are ligands, and again, those are Lewis bases, as we've been talking about. So here, chloride, ammonia are some good Lewis bases. What makes a ligand is something that has at least one unshared pair of valence electrons. And as I mentioned before, since they are somebody that's going to donate those pair of electrons, typically speaking, it is some type of polar molecule that has some non-bonding electrons. on an electronegative sort of atom, and also definitely things that have a negative charge. As I mentioned earlier, again, if you have a negative charge, it means you have some excess electrons, and then you have something to give in that particular situation. Again, if we look at ammonia here, on the nitrogen, it has that electrons, and here with the chloride, again, with the negative charge. We could think of the cobalt in this case as being more like the Lewis acid. Again, it has a positive charge here, which makes it electron deficient and willing to accept those electrons as they come in. Now, when we talk about these ligands, there are different types of ligands. And when we talk about the coordination number is the actual number of atoms that are bound basically to the metal in the complex ion. So if we look back there at the previous page there, where we have this guy here, when we look at this setup of this complex ion, it is the nitrogen here on this NH3 that's really attached. It is this nitrogen, is obviously the chlorine here, and it is just the nitrogen. So when we look at this arrangement, directly attached to the metal in this particular case are 6 atoms attached. The coordination number here would be 6 in this case, 2 for the chlorines and 4 for the nitrogens that are part of ammonia in this case. Now, when we talk about ligands, there are different types of ligands. So what we just saw there in that example, and a lot of ones that we've kind of seen along the way here, things like water, ammonia, chloride, bromide, and the halogens, those are all what are referred to as being monodentate or unidentate. And what that means is for every sort of molecule of those guys, they basically only attach to the metal in one place. So here they only attach in the water through the oxygen, and here only through the nitrogen as well. And there are some ligands that can attach in multiple places per sort of ligand. Most common one is ethylenediamine. Ethylenediamine is oftentimes abbreviated with an EN. So a lot of times in this coordination chemistry, you will see an EN written, and that is the abbreviation for ethylenediamine. It actually is used both in the formula and also the name. So sometimes people will use it kind of in both places as the abbreviation. Ethylenediamine looks something like this, I think. We draw it out. And this got a couple of hydrogens there, a couple of hydrogens there. And in this case, basically what it has for every one of those EN molecules, if you will, it basically has a nitrogen that has some lone pairs on it. And what that means is for each molecule of that you have, when it goes to attach to this metal in this complex ion, you're going to get basically a 2-for-1 situation. So for every one of those molecules, you'll basically have 2 binding points into that metal through the nitrogens. And again, if we put 2 of them on here, for example, again, we're going to get some attachment happening here on the second one, same spot, through the nitrogens here. And we would get, again, another attachment here happening, a 2-for-1 deal. So if you had this written, it would look something like this in the formula, for example, whatever that metal might have been, it would look something like this. And very commonly when people are asked to sort of give the coordination number, sometimes what people do is they look at the formula and go, oh, it's got to be like that number that's down here. And in this particular case, it would not be the number here because as you can see here, it is attaching in 1, 2, 3, and 4 places. The coordination number here would actually be 4 for this guy because the actual ligand is bidentate, which means it can attach in 2 places. So sometimes people get into a bad habit when they're trying to sort of give out the coordination numbers, looking at the formula and just kind of taking the subscript, you will get the right answer if it's monodentate because it only binds in one place per molecule. But definitely if it's something that's bidentate or polydentate, you will be in trouble. You won't get the right answer. So I would say ethylenediamine is probably a very common bidentate. The other very common bidentate one that you come across a lot is our friend oxalate, is the other sort of bidentate one that's very often found and seen. And again, if you drew, here it goes. Just come back. If you drew oxalate, it will look something like this. And this is oxalate, and it's again, for every molecule of oxalate that you have, it is this single bonded oxygen here on each side that is where it will attach to the metal. So once again, you do get, much like the ethylenediamine, you do get a 2-for-1 situation happening here where it will attach basically through both of those oxygens to the metal. So you do have to sort of adjust it. Again, oxalate and ethylenediamine, probably your two common bidentate. There are others, but those are very common ones. There's also things that can attach in multiple places per ligand, and probably the most common one is EDTA. EDTA can actually bind in 6 places per one molecule. So EDTA can really surround that metal and kind of grab it up through 6 different sort of locations on it. And that's what is known as being polydentate. There's some that can do 3 as well. So there are some varieties here, and that's why you want to think about the coordination number correctly. It does depend on the ligand as to what you may end up with. Any questions on that there? Yeah. Yeah, I would say these are probably some of the main ones. We're going to see a table shortly that'll have them listed, but these are pretty much mostly the main ones, yeah. Are most common ones that you come across. Now, how do you know, for example, how many ligands you may get attached in a complex ion to the metal? And it does have to, a lot of times to do with the charge of the metal. So typically things that have a +1 charge, as you can see here, will very commonly go more of a 2 in terms of ligands, maybe some 4, or a 2 to 4 sort of situation of how many ligands they could attach. When you get a greater positive charge like you have over here, a +2 charge, you will start to see more of a 4 to 6 sort of attaching. And if you think about it, right, the greater the positive charge, the more electron deficient the metal is going to be, and the more apt it's going to be able to accept kind of more electrons, right? The greater the positive charge, because it's missing more electrons, obviously, to become that positive charge. And here with 3s, typically we end up with a coordination number of 6, except for gold. Gold will kind of hang out at 4. But again, sort of the greater the positive charge on that metal that's in the complex ion, usually it's able to accommodate, for example, more ligands to attach. So here again is our ethylenediamine that can attach there. This is our EDTA, and again, as I mentioned, it can attach in 6 different places. 1, 2, 3, 4, 5, and 6 places. So one molecule of EDTA can really surround a metal really well, and that's why it's sometimes referred to as a chelating agent. Chelating agent are bidentate or polydentate sort of ligands because it can really surround the metals really well. Sure question. You have to figure it out based on the complex ion that's there and the ligands that are there. Yeah. So in a sense, yeah, you have to kind of be familiar with the type of ligand. Is it monodentate, bidentate, so that you can calculate it correctly. Yeah. Other questions? All right, so these are sometimes referred to as chelating agents, again, because they can really grab onto those metals. If you look at a lot of ingredients and stuff, you'll sometimes see EDTA listed. And again, it's just used there to kind of grab up some metals and stuff out of certain things. Here's a table, and I think you have a similar one in your book here. And again, as you can see, most of the ones we've been talking about are kind of the main ones. Again, a lot of monodentate ones: water, cyanide, ammonia, nitrite, thiocyanate, hydroxide, and the halogens. Those are all typically monodentate. That means if you have any of these guys, it's a 1-to-1. For every one molecule, you get one connection or coordination number, if you will. Bidentate, again, are two common ones here: oxalate and ethylenediamine. That is, again, for every one of those, you get a 2 for one. So you get kind of two coordination number countings for every one molecule. And here's diethyl endyltriamine. Triamine means amines are the NH2s. So it has 1, 2, and 3 places. I totally circled the wrong one there. Let's go with the nitrogen maybe on that end. And again, in this case, this guy would be able to attach in 3 places per molecule, each at the nitrogen, which has the non-bonding electrons. And that guy here, for example, you would get a 1-to-3 sort of coordination number. So for every one of those, you would get basically count 3 for the coordination number. And then here's our ethyl endyl. This is our EDTA down here at the bottom. Again, 6 different spots where it will attach. By the way, kind of a -4 charge overall as well. There we go, happening here. All right, so why don't you take a moment here, and what we want to know is what is the oxidation numbers for the metals in each of these coordination compounds. And by the way, typically when you see these guys written like this, these coordination compounds, typically speaking, the thing in the parentheses or brackets, if you will, is the complex ion, and the other guy is the counter ion. So why don't you take a moment, and the one in the brackets, what we want to figure out is what is the oxidation state of the metal that is there. Again, okay, let's take a look at this one. So as I mentioned before, typically speaking, when you see a coordination compound written, a lot of times they will put kind of brackets around the complex ion part. So when we look at this part here, the first one, which is KAuOH4, this part right here is our complex ion. And that would mean here the potassium actually would be our counter ion in this particular case. So we're looking for the oxidation state really of the gold here. So what we do know is hydroxide is -1, and there's 4 of them, which would give you a -4. On the outside here, we know potassium is +1. So we got +1 and -4, which means in this particular case, our gold is rolling with a +3 charge. Questions on that there? Obviously here, a coordination compound is neutral, so there's no overall charge, so everything needs to add up to 0 in this case. If we look at the second one here, once again, in our brackets here would be our complex ion. And this here, the nitrate, would be our counter ion in this case. And again, kind of going through it, NH3 is ammonia, and ammonia actually is neutral, right? No charge, so that's a 0. On the outside, though, we have NO3, which is NO3 minus, which is nitrate. That's a -1 charge. And there's 3 of them, which would give us a -3 in this case. Once again, here, that would mean that the chromium would be an oxidation state of +3 in this particular case. First off, any questions on how to identify the oxidation of? Yeah. There's no rule. The rule is with coordination compounds, as I mentioned earlier, is it will follow kind of like an ionic compound. And that means it's always the positive guy first, followed by the negative. And the complex ion can be positive or negative, and the counter ion can either be positive or negative, depending obviously on the complex ion. So for example, if we look at the arrangement here, the first one, just by the way it's arranged in the formula, we know the counter ion is going to be positive. We know overall in this case, the complex ion is going to actually be negative. So if we were to just take the complex ion part of this compound out, which would be something like this, we know what, based on what we just did, that that's -1. That would get us a -4. We know that the gold is +3. And that means that in this particular case, the actual complex ion part has an overall charge of -1. And that's also why when we look at our counter ion here, we actually only have one potassium, which is +1. And again, it's pretty much like an ionic compound. It's got to kind of equals 0 in most cases. So that +1 -1 is why we get to 0 and why the form we only have one potassium, stuff like that. As opposed to if we come over here, and again, we just pull out this sort of complex ion part. We got here CrNH3 6. And once again, the ammonia is going to be 0. Based on what we did earlier, we know the chromium here is +3. So in this particular case, this complex ion actually has a +3 overall charge, which again is why it comes first in the formula, followed by our counter ion that's negative. That's also why when we look at the counter ion in this case, we have not just one nitrate, not two nitrates, but we actually need three nitrates there, again, to counter that +3 charge. So that is why we end up with the three nitrates on the right-hand side here as our counter ion in this case. And again, just based on the sort of location of each of those in the formula, you'll know really if your counter ion or complex ion is positive or negative, just like your counter ion is positive or negative. And again, you could have either one in either situation there. Questions on that there? All right, why don't we take a... Okay, we're going to continue on then. Any questions so far on what we've been talking about? Okay, so now that we got sort of the idea here of our coordination compounds and identifying oxidation states, the next thing we're going to actually talk about is kind of nomenclature of it and naming coordination compounds. There's some interesting sort of things that go along with this. So let's talk about some of the rules here when we name these coordination compounds. As we've been talking about, again, you can kind of think of it as an ionic compound and always the positive guy first and then the negative. So really always the cation before the anion. As I mentioned earlier, that does go for both the name and also the formula. That's sort of how it should go. Within a complex ion, the ligands are named first in alphabetical order, and the metal is always named last. So when you're naming the complex ion part of your coordination compound, you will go with the ligands in alphabetical order. This will be regardless of prefix. So there may be some prefixes that are used for ligands if you have multiple of the same ones. We don't look at the prefix. We actually just look at the sort of letter, the ligand's name, and go alphabetical on it. The complex ion part of the name, the metal part should always come at the end of the complex ion part of the name. Now, that does not mean that the last part of the name itself will always be the complex ion part or the metal part. But wherever the complex ion part is, because it could be positive or it could be negative, when you're naming that part of the name, should always have the metal at the end of that part name. So that's always where the metal should come. Some of the negatively charged ligands will end with the letter O. Some neutral ligands will be called by their normal name. And then there's a lot of guys that have kind of weird sort of special names that are used for them. For example, water is aqua or aqua, sometimes people will use. CO is carbonyl, NH3 is amine. Now, when we do have, as I mentioned before, sometimes like we saw in some of those examples, we have like a couple of chlorides attached or four ammonias attached. We do use Greek prefixes di for 2, all right, tri for 3, tetra for 4, penta for 5, hexa for 6. And that is used to indicate the number of the ligands that are attached. Again, if you had something like hexachloral, you would actually look at the C, not the H, again, if you're doing the alphabetical order part of it. So you don't look at the prefix when you're sort of doing that. Now, to sort of further complicate some of the interesting part of it is if the ligand itself, in the actual name of the ligand, already contains a prefix, then we use bis, which is for 2, tris, which is for 3, and tetrakis, which is for 4. So a very common example would be that EN one that we saw earlier. That's ethyl endyl diamine. So in the actual name of the ligand, it has the di part of it. So if you had multiples of those guys, you would not use di or tri. You would then go to bis or tris because the ligand itself already has a prefix in it. Or even the other one we saw that it was like triamine. You would use, again, one of these type of prefixes. I will say that oxalate, sometimes people will use these prefixes instead of the di or tri, and sometimes people will use the di and tri. So because oxalate's a bidentate, sometimes people will kind of use the bis and the tris with oxalate, or the other ones as well. But typically speaking, it's reserved for those that already has a prefix in it. The oxidation number of the metal is written in a Roman numeral that again follows the metal part of the name. So as we just talked about, wherever your complex ion is in the naming part of it, you should have the metal at the end of the complex ion part of the name. And you should also have a Roman numeral. Now, this is also something that's a little bit different than sort of normal naming, which is even things that have sort of like fixed charges, we still put a Roman numeral in there. So things like silver, where we don't usually put a Roman numeral, we will still put a Roman numeral. Things like zinc, where we typically don't because that makes a +2 charge always, you still would put the Roman numeral in this situation. Also, something that's really weird as well that occurs in certain situations is your metal could be neutral and you would put a 0 in there instead of a Roman numeral. So you will sometimes see that as well, which is kind of an interesting thing. So you'll sometimes see, obviously it's not a Roman numeral, but you'll see kind of 0 written, again, because your metal could technically end up being actually neutral in some situations in this case as well. Now, probably the weirdest thing that maybe occurs when you're naming these things has to do with the complex ion, and it has to do with whether or not your complex ion is positive or negative. Now, if your complex ion is positive, when you go to name the transition metal or the metal, you just use the regular name. So if it's copper, it's copper. If it's iron, and so forth. If the complex ion that you're going to sort of name is actually negatively charged overall, like we saw in the previous example, you actually will go with a name that ends in 8, and it's more like the old school type of naming. So instead of copper, it'd be cuprate. Instead of iron, it'll be ferrate. It'll be plumate, zincate. So you go with kind of like an older school name if the complex ion is negative, and it usually will end in 8 at the end of it. Again, regular old name if the complex ion is positive. Now, here are some ligands, and again, you can see aqua or aquo, amine, methylamine, carbonyl. And then our halogens are named very much like we do in organic chemistry: fluoral, chloral, bromo, iodo, hydroxo there for hydroxide, cyano there for cyanide. And here are some of those older sort of school names, if you will. Again, you would go with this type of naming if your complex ion is negative. So we have ferrate for iron, cuprate, plumate, argentate, arurate, and stannate. Again, you can see that all in the kind of ATE and kind of the root type of name of those guys. Here are a few more sort of ligands: chloral, bromo, hydroxo. If you have carbonate, a little carbonato, a little oxalato. If you're ordering some coffee or something like that. You got some aqua. And again, this is our EDTA over here. And you can see that is not quite the abbreviation going on there. And again, our ethylenediamine, as I mentioned earlier, that one is super commonly abbreviated with the EN. And again, people will use that EN again, both in sort of the name and also the other as well. So for example, if we go back to a couple of these here that we did. So let's take a look, for example, at this first one here that we just kind of looked at. So when we go to name this, we can, based on the location of everybody, as we talked about, sort of identify, for example, whether or not our complex ion is going to be positive or negative. And in this particular case, we know that our complex ion is going to be negative. The good news about the sort of counter ion is we basically just use the name of the counter ion. It doesn't really matter how many you have of them. So you will basically just use pretty much the name of it. Kind of like, for example, if we had K2O, that would be potassium oxide. And the same idea here. So if we were going to start out with this guy here, we would go with potassium, which is, again, pretty much just the name there of our complex of our counter ion. We then have 4 hydroxides here. So again, we would go to our list and we would find hydroxide, which is right here. That is hydroxo. And 4 is tetra. So that would be tetra hydroxo. Again, in this case, we do know that our complex ion overall is negative. So here we would not use gold. We would want to use, as we saw in that chart there, this right here, we would want to use sort of the older way of naming gold, which would be R-urate. So coming back here, this would be R-urate Roman numeral 3. So when we look at the naming of this on the back end here, because our complex ion is negative, this is really the complex ion part of the name. And what we were talking about earlier, where we see the metal part should always come at the end of the complex ion, that is what we see here, the metal part coming at the end of the complex ion name. And this would be potassium tetrahydroxo R-urate 3. Rolls off your tongue like there's nothing there. Why don't you try the other one that we did? Why don't you give the name for this guy here and see what you come up with? Yeah. The complex ion part is negative, and one of the rules that they have for naming these guys is if the complex ion part is negative, then you have to go with that old school type name. Yeah. But overall, in this particular example here, this coordination compound is neutral because we have the potassium as our counter ion. Yeah. Earlier, kind of dissected what we needed. By the way, you might want to do that when you're doing these to figure out, the oxidation state of the metal, is it positive or negative? Again, from just the arrangement of the formula, we do know, as we determined, that our complex ion here is positive, our counter ion is negative. That means that we can just use the regular name for the metal in this case because the complex ion part is positive. We do have 6 ligands here, and that's going to give us a hexaamine for our 6 ammonias. We will use just the regular name of the metal, which is chromium, and we do need our Roman numeral, which is 3. And once again here, as I mentioned before, typically with the counter ion, regardless of how many you have, you're just going to use basically the name of it, and this would be nitrate. Again, no prefixes on the counter ions, and this would be hexamine chromium 3 nitrate. Any questions on that? Yeah. You actually do. It's okay in this type of naming and stuff. Yeah. So we don't typically drop it like we kind of do on the other ones. Yeah. Other questions? Now, for example, if we wanted to know the coordination number here, right, of the first guy. By the way, the coordination number here of this guy would be 4, as each of the hydroxides are monodentate, which means they will attach in one place per molecule. The coordination number here for this guy would be 6, as again, each of the ammonias are going to attach to the nitrogens here. And again, since we have 6 ammonias, 6 nitrogens, coordination number here would be 6. In this case, it does match the subscript, and that's because these guys are monodentate, so they get basically a 1-to-1 sort of coordination number per molecule. And again, remember that if it is bidentate or something like that, you would not have that. Now, what would happen if we wanted to just name the complex ion without the counter ion? It's not a coordination compound. We just have, for example, just the complex ion present, and we want to give his name. We basically give the same name except for the potassium. So this would be tetrahydroxo rurate 3, and then we simply would just put ion at the end again. So if you don't have the counter ion, you basically would name it the same way and just kind of put the ion in it. Same thing here. If we were just doing the complex ion part here, that basically would be up to here, hexamine chromium 3, and then you would just put the ion at the end of it. So if you do have to name just a complex ion by itself, you basically name it the same way, just put ion at the end. And obviously, if it is a negative complex ion, you still go with the ATE ending. If it's a positive, you still go with the regular metal. Any questions on that there? All right, let's try a few more here. All right, so why don't you give this one a go and also figure out the coordination number. We know that that should be our complex ion. That would make the potassium here our counter ion. So we do want to kind of figure out oxidation states and all that, because obviously we need that for the naming. So this is oxalate, which is -2. There's 3 of them, gives you a -6. On the outside, we have potassium, that's +1, but there's 3 of them, gets you a +3. +3 -6 is -3. That means here the chromium is going with a +3 in this particular case. The coordination number on this one is actually 6 in this case. And it is 6 because oxalate is a bidentate, which means you get a 2-for-1 situation. So since we have 3 of those molecules, each one will attach in 2 different places per molecule. So 3 times 2 would give you a coordination number of 6 in this case. First off, any questions on that so far? All right, so the good news is we can just roll with the counter ion's name, which is potassium. We also know, based on our positioning here, that our complex ion is going to be negative. And again, that's because it comes second. So here, if we were to pull it apart, we actually know that this guy is going to be rolling with a -3 charge, and that's balanced out by the 3 potassiums in this case. So we are going to go with the kind of older name there for the metal. So that's going to be something like chromate, ATE, instead of chromium in this case. We also know that we have an oxidation state there of 3, so that's going to be chromate 3. We have oxalate here, which is oxalato. And in this particular case, we have 3 of them, which is tri. And we can now kind of put everything together. This would be potassium trioxalato chromate 3. Again, as I mentioned earlier, with oxalate, people do kind of use the other prefix with it. So it is possible that you would see somebody name this guy tris oxalato chromate 3. And again, I think it's because oxalato is bidentate, so sometimes they'll use that kind of tris bis sort of a connection rather than that. Or you can go with tri. I'll take either one on this one particular one. Yeah. And the questions on that name there. Yeah. All right. All right, a couple more. First one, name. Bottom one, we'll go with formula. Here's a few more metal names in case you need for reference. First one here, we see our complex ion there coming first, so we do know it's positive. This would be our counter here, coming second, which would be negative. Doing a little oxidation state here. Water is 0. Chloride here is -1. There's 2 of them. Gives you a -2. On the outside, we also have a -1. So that's like a -3. So here, the chromium would actually be a +3 in this particular case. Any questions on how to get to that there? Also, if we're looking at coordination number here, we have 2 monodentates there and 4 monodentates there. That's a coordination number of 6 in this particular case. Because our complex ion is positive, we could just use chromium as the name of the metal. We don't have to worry about the other way. We are going to go with our ligands here. So we got 4, which is tetra aqua or aqua, whichever way you want to go with that. We have 2 of the Cl's, so that's going to be dichloral. And again, here we go alphabetical. As I mentioned before, we're not going to be looking at the prefixes here. So when we're going alphabetical, we're comparing the A to the C here. So the A is going to come first in this case. Again, we're not going to look at the prefixes for alphabetical order. That then means that my metal should come at the end of my complex ion part of the name here. So a little tetra aqua, dichloral, chromium, Roman numeral 3. And once again, we will just name our counter ion like normal. Here, the chlorine comes second. So it is like an ion. So it is named like the ion of chloride in this case, IDE at the end of it. So a little tetra aqua dichloral chromium 3 chloride rolls off the tongue nice and easily. Any questions on that name there? All right, in this case on the bottom here, we actually have the name and we want to write the sort of formula. So tris is 3. Ethylendyl is our En. And as I mentioned before, you basically can use the abbreviation. You can also write out the formula of the CH2, CH2, and H2 twice. But we'll just go with that. Cobalt, Roman numeral 2 there. That means I have a cobalt with a +2 charge. And again, I do know that this front part here is my complex ion. And that is because, once again, at the end of this part of the name is the metal's name. So we have cobalt at the end. So we know always the complex ion will have the metal at the end of its name. So we do know that it is coming first here. And cobalt's the regular name, which tells us it is going to be a positive complex ion. So just putting together our complex ion part, we will have something that looks like this. And in this particular case, the cobalt is +2. The En is 0. So overall, our complex ion part actually has a +2 charge. And that's really important because when we go to our counter ion, we have sulfate. And sulfate is actually a -2 charge. So because we now know the charge on the complex ion is +2, we know how many of those counter ions we need, which in this case, we actually just need 1. And we will end up with something that looks like this in this case. By the way, the coordination number here would also be 6 in this case. Again, this being bidentate, so you get a 2 for 1 on that deal. So again, because there's 3 of them, each one attaches in 2 places, gives us a coordination number of 6. Any questions on that formula there? And again, like I said, you could write out the formula for En if you like and put it in there. Okay, so let's take a look. Again, starting here with the first one, we see our complex ion there and our counter. So here on the first one, we are going with a positive complex ion. We got 0 for the ammonia, -1 for the chloride inside the complex ion. We also have 2 chlorides on the outside. So that's going to give us really a net of -3. So the cobalt here is going to be +3. By the way, the oxidation state will not always be 3, just happens to be in these examples. Uh, the coordination number here is actually 6, as we got 5 and 1 there. And now we could get to our naming. We have 5 of the ammonias, so that's going to be pentamine. We have 1 chlorine inside the complex ion. We actually do not use mono here on these names in terms of a prefix, so we just call it chloral. And here we're going to go with just a regular name, cobalt, Roman numeral 3 in this case. And again, our complex ion, our counter ion, we are just going to name it kind of like normal. In this case, the chlorine is coming second, which means it's negatively charged. So it should get the IDE treatment there at the end. And it should be chloride again. No prefix really on any of the counter ions either. So it doesn't matter how many you have of those guys. So this would be a little pentamine chlorocobalt 3 chloride. Any questions on that? Yeah. It is actually, yeah. So yeah, it's all one big old word, basically, yeah, all together. And then there's typically a space for the counter ion either before or after, depending on it. Yeah. Other questions? All right, so let's take a look at the second one here. We have counter first, complex ion second. That automatically tells us we got a negative complex ion going. That also will tell us we're not going to use iron as the name of the metal here. We are going to go with ferrate, which is kind of, again, that older school type of name. We'll figure out some charges here. So that's cyanide, which is -1. There's 6 of them, which is -6. There is a +1 for the potassium, and 3 of them is a +3. So once again here, we got a +3 on the iron. We're going to go with just the counter ion name. And since it comes first and is positive, it's really just the metal name, potassium. We'll go with hexacyano for cyanide. And again, we're going to go ferrate, Roman numeral 3 in this case. Once again, since our complex ion is negative, we have our metal coming at the end of the name. Coordination number on this guy going to be 6, as cyanide is monodentate, so we'll attach in one place per molecule. So that is what we end up with in this case here. Any questions on any of those things there? All right, a couple more formulas here. Okay, so taking a look at this again, I know my complex ion part, which is through here, is definitely positive as it comes first. I also see just a regular name for the metal, so that tells me it is positive. I'm just going to kind of take the pieces of it and kind of put it together. So triamine means I have basically 3 ammonias. Uh, Bromol means I have a bromide, and a platinum 2 means I have a PT with a +2 charge. So if I kind of just put all that together here in my complex ion, I got PT, NH3, 3, and a Br. I again could kind of figure out what is that positive charge overall here on my complex ion. Again, this guy being +2, this being 0, and this obviously being -1. That means really in this case, if we just look at the complex ion part, we have just a +1. And that's important for my counter ion in this case, which is chloride, which is basically -1. That basically tells me that I just need 1 counter ion in this case. And we should end up with something that looks like that right there. Any questions on that one there? By the way, the coordination number on this one is 4. Yeah, coordination number on that one is 4 based off of that. Any questions on that one there? Taking a look at the last one here, I see potassium, and then I see cobaltate 3 at the end. So this tells me this is my complex ion part. I also know it's negative because obviously it comes at the end here. And that means that I could just start with the pieces here. Hexafluoral means I have 6 fluorines. Cobaltate 3 means I have a cobalt with a +3. Again, if that is basically my complex ion components, putting that together, again, I got a +3 here, -1, there's 6 of them, -6. That is actually going to give me a -3 overall for my complex ion in this case. That again is important for our counter ion here, which is potassium, K plus. That means I need not 1, not 2, but I actually need 3 of those potassiums to balance it out. That would get me K3COF6 in this case, right? Any questions on naming, writing the formulas, figuring out oxidation states, coordination numbers? By the way, coordination number on the last one is 6, yeah, as fluoride is a monodentate. Any questions? Okay. Good deal. Next thing we're going to talk about then are isomers, and isomers with these coordination compounds or complex ions. There's some different types of isomers. There are structure isomers, which have different bonds, and there are 2 types that we're going to talk about, which are coordination or linkage isomers. There's also stereoisomers, which have the same bonds, but different sort of 3-dimensional arrangements, and that gives rise to cis and trans isomers or optical isomers. We're going to go through each of these here. We're going to start with coordination isomers, and when we look at coordination isomers here, the idea of isomers is, in general, it is something that has basically the same chemical formula, but pretty much there's some type of different connectivity that happens. And because of that different connectivity, it does give things different properties. So if we look at both of these, they both have a chromium. They both got 5 NH3s. They have a sulfate, and they both have bromine. So they basically are composed of the same things. Here, though, on the first one, this is our complex ion. And what we see on the first one is essentially we have our chromium, and it's attached to 5 of these ammonias. And also attached to a sulfate, if you will. And in this first case, it is the bromide that is the counter ion that's balancing this out, as overall here, this chromium has a +3 charge. This +3 charge and the -2 charge there gives this complex ion really a +1 charge. And in this case, the sulfate is actually part of the complex ion, while the bromide is actually the counter ion. And that's different than what we see here if we drop down to this guy, this being our complex ion. In this case, the bromine is actually part of the complex ion, and it's the sulfate that's actually the counter ion. So in this particular case, we have the chromium again attached to those 5 ammonias. But here it is actually attached to the bromine. And with this guy being a +3, this being a -1 essentially, that's going to give us a +2 overall charge. And in this case, it is our sulfate with its -2. That is the counter ion. So in coordination isomers, what happens is, in one case, for example, one of the ligands or ends up really not being a ligand is a counter ion. And in the other case, it actually is part of the complex ion. Any questions on that there? Now, linkage isomers are what happens when you have the sort of same ligand, but that ligand has the ability to attach in different atoms. So, for example, if we take nitrite, which is NO2 minus, Nitrite, because it does have the non-bonding electrons on the nitrogen, can bind in here through the nitrogen. And that's what we see here. The binding through that nitrite is actually through the nitrogen. But because it also has a single bonded oxygen, it could also choose to bond not through the nitrogen, but also bind in through the oxygen. So these are going to be linkage isomers. They're going to have basically the same formula. The difference, though, is how the ligand is actually attaching to the complex ion, or the metal in the middle. In the first case, is attaching through the nitrogen. In the second case, is attaching through the oxygen. It's important to keep in mind here that it is still attaching in only one spot. So they're not both attaching. So this is not like a bidentate sort of ligand. It just has the option, if you will, that in some cases, maybe the oxygen gets in there. In some cases, the nitrogen can get there. So it has sort of choices as to how it can attach as sort of one attachment point to the metal. So a linkage isomer, the difference is within the actual ligand of how it attaches to the metal. And you might have a multiple options like a nitrogen or an oxygen that can do it. Once again, here, they're not going to both do it. Just one of us is going to do it in this case. Any questions on linkage isomers? Now, stereoisomers can be geometric isomers, which give rise to cis and trans isomers. And cis and trans, you'll learn a lot more about that in organic, but in general, cis and trans, cis means really the same side, and trans means kind of the opposite side. And in organic chemistry, a lot of times what we're talking about is like a double bond. Are the things on the same side of the double bond or on the opposite sides? But here we're kind of talking about the plane of the molecule of the complex ion where they're at. These guys also, again, have basically the same formula or the same sort of elements involved in the formula. They have the same bonds, but different bond angles. This is common in square planar complexes. Square planar is right that expanded octet where it basically makes a nice little square in within the plane, as you can see here. So here we have cis PT NH3 Cl2, and here on basically the same side of the plane of the molecule, we have the ammonias, or you could even look at the chlorides if you like, the same size cis. Down here we have opposite arrangement here of the chlorides. You could also look at the ammonias as well, opposites, and that would give you your trans. So within sort of a square planar sort of geometry here of a complex ion, what you're looking at is either they're kind of both on the same side or kind of opposite sides of each other, would give you rise to the cis or the trans sort of isomer of this guy. Now, when you have a more octahedral arrangement like we have here, what we see here is trans and cis. So in A, this is the trans, which means if we look at the chlorides here, you could kind of think of it as one being above and below the plane of the molecule, the kind of the central plane there. So you got kind of one above and below, and again, that would give you more of a trans, as you can see here, top and bottom, if you will. On the cis, it's going to be, for example, these chlorides kind of within the same side here. So you can kind of see it's kind of all within the same side. They're not opposites of each other in terms of their arrangement. This is, by the way, more of an octahedral arrangement of geometry, which again is the expanded octet there, where you have kind of 6 electron pairs and 6 bonds. Now, optical isomers are isomers that have the opposite effect on plane polarized light. And if you have a chiral molecule basically has a mirror image that is non-superimposable. So the most common sort of example of that is your hand. If you hold up your hand to a mirror, you get your other hand staring at you, basically. Yeah. And if you pull out the mirror image, which is your other hand, A chiral molecule has non-superimposable mirror images, which means you could rotate this thing all the way around as much as you want. You will never get it to sit correctly. So for example, if I go this way, I got thumbs on the right side, but the palms up, palm down. That's not correct. If I flip it, I got palms down, but thumbs are on the wrong side. So you can do whatever you want. You'll never be able to kind of rotate a chiral molecule in a way that it will fit perfectly the mirror image over the original molecule. And it's really because there's some type of bond that occurs that's different when it reflects in the mirror than what the original molecule are. These type of isomers are sometimes referred to as enantiomers. Um, and with plain polarized light, you could send it through. You can also measure the angle of rotation. We're not going to get into any of that stuff though, but there's our hand and our rotation there. By the way, something that is achiral is something where if you put a mirror image up and pull out the mirror image, you can rotate it and get it to fit perfectly over the original sort of molecule. So chiral molecules though, they have some type of bond that kind of screws it up. There's always something that's off with the rotation that occurs. Um, so clearly here, let me just kind of hang on a sec here. All right, so if we look at this here, we have isomers 1 and 2 are mirror images. They're identical and cannot be superimposed. Again, if we look at this, what ends up happening, it's really hard to sometimes visualize what's going on, but this is our original sort of molecule as it gets reflected into the mirror. Again, this kind of goes to here, this goes to there and so forth. But what ends up happening is in the original molecule, we have this connection between the nitrogen here and the nitrogen that is like right here up in front. So we got this connection, between these two. But when this gets reflected, what ends up happening is this guy gets reflected to here. This bottom guy gets reflected to here. But this guy gets reflected to the back. And when he does that, he takes that bond with him. And now that bond that was right in front originally is now really in towards the back. So when you pull out that mirror image, you end up with this bond here that is in a different sort of location than the bond that was originally there. So what happens is if you try to take that isomer 2 and rotate it, there's always going to be something that is basically not going to fit perfectly, because when this got reflected, this guy kind of took its bond back to the back of the mirror, and something's going to always be off. So these two guys are chiral. They're mirror images that are non-superimposable, again, because it kind of shoots that bond in the wrong location to the original one. Now, if you look at this one here on the right, this is our trans. And when we get this guy reflected, this guy reflects here, this guy reflects back, reflects. But what ends up happening actually is we actually don't mess up any of these bonds. So we actually still have really these bonds in the same location. That means, again, when we pull this guy out, we are going to be able to superimpose that mirror image. Everything will line up because of that in this sort of trans. But again, if we take the cis isomer and we want to do that, once again, as we saw in the previous one, when this guy gets reflected back here, he's going to take that bond once again to the back, and that bond there that's going to create the mirror image is not going to allow it to superimpose. So in a lot of cases, a trans isomer can superimpose on each other because it's able to kind of maintain those connections. And a lot of times when you have a cis isomer, because of the way it gets reflected into the mirror image, which is sometimes hard to visualize in your head and kind of visualize it, you get this kind of shifting of a bond to a different location. And because that, as you kind of rotate it, that bond's always going to just be out of line with the original guy. Any questions on that there? Now, enantiomers, as I mentioned, are two molecules that have mirror images that are non-superimposable. They're really chiral. Sometimes drugs have isomers like that, and only one of them are effective in whatever they're used for. Now, the last thing we're going to kind of talk about in this chapter is sort of the bonding and electrons and geometry that occur with complex ions, and what happens to sort of those electrons that are in the metal and how they get distributed. Now, because of these complex ions and because of the ligands that are attached, the electrons in those transition metals, based on the geometry, does get distributed differently depending on the ligands that are present. Now, the formation of hybrid orbitals to share electrons, if you remember hybrid orbitals, right, we have sp, right, sp2, sp3, sp3d, sp3d2, right, a little expanded octet. Those hybridizations, right, go with our electron pair geometry, right? Typically speaking, that is linear, that is trigonal planar, that is tetrahedral, that is trigonal bipyramidal, and that's like your octahedral sort of situation. Now, Vesper model doesn't work extremely well for complex ions. The interaction, as we talked about, is sort of more thought of as we've been talking about, sort of Lewis acid base type of situation is going. Hybrid orbitals are used by the metal, depends on the number of ligands that are present. So here again, we have a coordination number of 6, and that typically goes with our octahedral geometry. And again, we got our electrons coming in from our ligands into our electron deficient cobalt in this case. We can have sp3, which is tetrahedral geometry. We could also have sp3, which is square planar geometry, and our coordination number 4, which is square planar. Not really sp3, but sp3d. And we do have linear, which is sp in this case. So there is a relationship between the coordination number and typically the geometries that we see in these complex ion. Coordination number of 2 is linear, kind of like sp. Again, coordination number of 4 could either be tetrahedral or square planar, and typically those with a coordination number of 6 will roll with the octahedral arrangement in terms of their geometry. Now, when we look at our transition metal, and this is what we're talking about here, is really our transition metal. As we talked about, they basically are d orbitals, right, involved. And there are 5 different d orbitals, obviously, and each one could obviously hold 2 electrons, 2, 4, 6, 8, and 10. And in the absence of any ligand, all 5 of those d orbitals on an energy level will actually be equal in energy. So all 5 of those d orbitals within the transition metal will be equal in energy. And what that affects, for example, if they are equal in energy, is they will follow normal sort of electron filling, which, as we know by Hund's rule, is maximize parallel spin, which means they will all go in one at a time, right, before they come back and start filling up the rest of them and pairing off the spins. But what happens when you actually introduce, for example, ligands into the mix, you get some what is referred to as splitting of these d orbitals, and this is what is sometimes referred to as crystal field splitting. By the way, what we are looking at here is a coordination number of 6 and an octahedral geometry type of situation. So these are our isolated transition metals here, d orbitals. And with the presence of the ligand, what we end up getting are these 3 d orbitals going lower in energy and these 2 d orbitals going higher in energy, kind of the squared ones going higher in energy. The difference between the lower d orbitals and the higher d orbitals is what is known as crystal field splitting. So that's the energy difference. It is sometimes abbreviated with a delta symbol. You could actually calculate that just using the regular sort of energy equation. So how this is affected? Well, what's going to happen in this situation is, depending on the ligands that are present and depending on how many electrons you have to distribute for your metal, in a certain situation, what might happen is we may see the splitting occurring where the difference here is relatively small in terms of the crystal field splitting. And as that case would happen, the electrons would distribute themselves kind of like normal. They would go to the lowest energy d orbitals first and go, and that's not a big difference between the guys that are up there. We'll actually go up here and just kind of start feeling like normal. So they'll kind of feel like normal. But now in certain situations, what could happen is there could be a dramatically drawn right here, a much larger sort of splitting that's occurring between the d orbitals here. And that's going to affect how the electrons get distributed. And what will happen is the electrons will go here and feel like normal. And at this point, what they'll decide is that's like way too high. I don't want to go that high. I would rather feel down here first until I'm absolutely forced to go to the top. And the result of this is what will happen is it will give some complex ions, what is sometimes referred to as a different sort of a spin. And you could either have high spin or low spin complexes. And that's based on how many unpaired electrons you have. And that's a very common sort of question that's asked on these is, how many unpaired electrons would this complex ion have? The lot more unpaired electrons you have is typically referred to as a high spin complex. A lot more paired off electrons, where they're going in opposite directions, is what is referred to as a low spin complex. Electrons, right, have spin, right? It's a spin quantum number, and they're affected, right, by electrical field, magnetic field as well. You can distribute those electrons by just a little bit of energy, and you could actually calculate the crystal field splitting by using the regular old equation you might remember, which is E is equal to H times the frequency, H being our friend Planck's constant, 6.63 times 10 to the minus 34 joule seconds. And that is our frequency, right? Not to be remembering our other friend, C is equal to the wavelength times the frequency, where C is the speed of light, 3 times 10 to the 8 meters per second. A reminder that you can use both of those together. Just a reminder that if you solve for the frequency, that is C divided by the wavelength, and you could substitute that into hc over the wavelength. That means if you know just the wavelength, h and c are constants, you can figure out the energy of the splitting of the lower energy d orbitals and the higher energy d orbitals. Or if you know the frequency of that, you could also figure that out as well, right? And one of the things that we've done over the semesters, right, is maximum wavelength, right, is where we want to set our wavelength to. Remember that the color, for example, of the solution that we see is not really the color we would set our wavelength to, because that is not the wavelength that's being absorbed. It's actually the complementary color, right, to the color that we actually see is what's being absorbed. So we'll take a look at this. I think it's actually filled in on your notes, so we'll just kind of go through it, just talk about where we get everything. So the absorption maximum for this complex ion occurs at 470. What is the color of the complex, and what is the crystal field splitting in this complex? So once again, at 470, that would put us here at blue. Again, the solution should appear the complementary color to us, and it would appear orange in this case. Again, if we were measuring absorbance, we would set it to blue in that 470. We could use our equation here, which again is our energy. We're going to go hc over the wavelength since we only have the wavelength given to us. Remember that nano, right, is 10 to the minus 9. So we do need to convert our wavelength into meters so everything cancels out. This is our Planck's constant. That is our speed of light. And this is our wavelength, again, converted into meters. That way meters cancel, seconds cancel, leaves us with joules in this case. That's basically how many joules there is per atom. And if we want to know how many joules per mole or kilojoules per mole, we would use Avogadro's number. And that would give us how many atoms per mole. And the moles here will cancel. That would technically give us joules per mole, which then you can convert to kilojoules per mole. So this calculation is basically the same calculation as you did previously. Again, you could use it to basically figure out the splitting of those lower energy level d orbitals and the higher energy level d orbitals. Any questions on that there? Okay. So let's talk a little bit about how do we know if we will sort of get a big split or a small split in terms of our d orbitals. It has to do with the ligands that are present. This is the spectrochemical series. And on the left-hand side here, we have what are sometimes referred to as weak field ligands, which means that they will not split the d orbitals that much. And you would expect, this type of situation occurring where we would end up with a small sort of split, which means that our electrons would go in basically one at a time and then come back and pair up. Now, if you're on sort of this side, you'll have what is referred to as a strong field ligand, and that splitting is going to be relatively large. I'll just borrow this. And what that's going to end up doing is causing these guys to pair up more than go in one at a time. The result of this is you're going to end up with a lot more unpaired electrons in this sort of small splitting. And that is what's going to be referred to as a high spin complex. As opposed to over here, as you can see, you're going to end up with a lot more paired electrons. And that would be what is referred to as a low spin situation. Now, what happens in the middle, it kind of depends, but sometimes they may just tell you do it for like the high spin or do it for a low spin or strong field or weak field. And in some cases, they may not tell you any information. And the reason for that is it really doesn't matter. And for example, if you had this splitting and you did your calculation, you only had 3 electrons, you're not getting up there anyways, right? So it really won't matter. In some cases, it may not matter depending on how many electrons you have to distribute as to whether it's sort of weak or strong. They're only going to go to the bottom to begin with because you don't have enough electrons to distribute. So a lot of times in the middle here, they'll kind of give you a hint maybe if they want you to do one way or the other. Or again, if they don't really give you a hint, then it may not make a difference regardless of which way you do it. You'll end up with the same number of unpaired electrons. Any questions on that there? Let's take a look and see how this works. So let's just take, I don't know, I'll do the first one here. Let's take the first one here, which is our nickel with our bromine. So the first thing we really want to figure out is the oxidation state of our nickel. So in this particular case, we have bromine, which is -1. And there are 6 of them, which is -6. Overall, we have a -2. So in this particular case, our nickel actually has a +4 charge. Now that's really important because if we look at nickel on the periodic table, it's 28. And it has an argon 4s2 3d8 arrangement. With nickel with a +4 charge, as we talked about earlier, it will definitely lose the 2 electrons here from the S. It will also lose 2 electrons from the D, and it will leave it with argon 3d6. Now, those 6 electrons that are in the d orbitals are actually the ones that we want to distribute here in our little picture of our crystal field splitting of those d orbitals. By the way, the coordination number here is 6, which is the octahedral arrangement. And what that tells us is we are going to get the d orbital splitting like we just saw there with basically our squared guys up on top x squared, y squared, up there, and z squared kind of over here up on top, and obviously our non-square guys on the bottom. So what we have to look at now is the ligand that's here. And what we see is the ligand is Br minus. And if we go to our little chart here, Br minus is over here as a weak field. So weak field means that we're going to get a small sort of separation that's going to occur. So what that means is when we go to distribute these 6d electrons that we want to distribute, they will go in 1, 2, 3, 4, 5, and then go 6. Again, because the separation between the lower d orbitals and the higher d orbitals are not that big. And we will end up here with actually 4 unpaired electrons. Question. This would be considered a high spin complex, as we have a lot of unpaired electrons sort of happening in this case. Questions on that there? So, okay, so let's take a look. So here we got cyanide, which is -1. There's 6 of them. Gives us a -6, overall -3. So our iron here is +3. So iron is 26. So iron with no charge. A little argon, 4s2, 3d. We'll get there 6, I think. And at this case, it does have a +3, which means that we are going to end up with these 2 gone, and we will have to take 1 out of there, and I'll end up with argon 3d5. So we do have 5 the electrons to distribute. In this case, though, our ligand is Cn. So taking a look at our little list here, Cn is a strong field splitting. That means when we take our kind of 3 lower guys and our 3 higher guys, we're going to get a pretty large splitting that's going to occur there. That means when we go to distribute these, they're going to decide after the first 3 that that's way too high. We'd rather just kind of come down this way. And that's going to end up with 1 unpaired electron. And this would be considered a low spin complex in this case. Questions on that there? Same thing here. If we just look at the couple more here, we got our nickel. Again, this is 0. That means the nickel here is +4. So as we saw before, we have 6 electrons to distribute in this one. And if we look at our En in this case, En is also hanging out towards the strong field. So again, we would expect perhaps a little larger of a splitting occurring. In this case, distributing our 6 electrons, 1, 2, 3, again, going to be too big, going to go and down this way. Watch, we end up with 0 unpaired electrons, definitely a low spin complex. Any questions on how to figure that out? So those are very common questions. You're asked to draw it, and also really how many unpaired electrons does these metals have, or complex ions have. Any questions on that there? That chart would be probably good. I'd probably give you something that's on there, I imagine. Yeah, good. All right, let's see here. By the way, again, what we're looking at with the 3 on the bottom and the 2 kind of squared guys, x squared, y squared, up on top is specific for coordination number of 6 and the octahedral geometry. Now, if we look at here is one of the ones we didn't do, but again, here with our F6, going to give us our high spin, a lot of unpaired electrons as a result of a smaller crystal field splitting. And here with a larger crystal field splitting, we're definitely going to get a lot more paired up electrons happening here. And there's our different combinations for our octahedral sort of arrangement. Now we can have for tetrahedral, and tetrahedral is a coordination number of 4 and a tetrahedral geometry. It is pretty much similar to what we just did with octahedral, except that they're flipped. So the squared guys are up on the bottom, two are on the bottom, and the other three are up on top. It would work the same way if you had a large field or strong field, it would just pair up here first. And obviously, if you had a smaller field, it would work its way through here and then come up here like normal before it paired off. So it works basically the same way. Again, that splitting here, but it's sort of reverse of the octahedral. Again, coordination number of 4 and tetrahedral will give you this type of splitting. Now, we could also have with a coordination number of 4 square planar, which is sort of like the expanded octet. You can see you get a little bit of weirdness in terms of the splitting that's happening here. So they do kind of go all over the place. But again, it would feel the same sort of way, kind of lowest as you went through there with, your kind of differences in energy happening in that particular case. For us, you will not be responsible for square planar. You'll be responsible for tetrahedral and octahedral splitting. So just those two. You don't have to worry about this guy here in terms of drawing him. Any questions on that there? All right, that wraps up chapter 20, they say. Yes. Good deal. All right, any questions on that there?